So today I'm going to have a tough time to draw on this Microsoft pen because I left my pen at the office. So currently I'm using my mouse to draw, so it's a bit difficult right now. I just realized I didn't bring my pen back actually, but it's too late already. So today is a bit going to be a hard time to draw on this. Okay, time is about. If you have a question, you can ask me. If you don't understand, I try to, my main focus is on the assignment number 2. I try to get you prepared for assignment 2 because the rest of the topics, is you can study yourself. I think it should be okay.
Okay, sir.
Only the AC we call the AC system phaser, AC phaser. The one probably I need to explain a bit to build up your foundation. Otherwise you'll have hard time trying to understand the content. I remember the time when I first exposed to this AC system. I think my professor he didn't actually show the details of all this calculation. He presumed everyone knows all this background, all this why we need this, why we need to do this, and what's the purpose of converting from here to here. The professor actually didn't explain in detail the purpose or the function of each system. He didn't kind of explain in detail. So today I realized it's better for the student to understand some of the basic why is appear this way, why we have to write in this format. If you know all the reason why you need to do this, probably it helps you to understand the rest of the topic. I think it's going to help you understand easily. If you just memorize all the methods, I don't think it's not efficient enough to learn the rest of the topic. Somehow you just need to find the right methods. So they say that when you come to the classroom, you are not trying to memorize something. You are not trying to memorize a topic or something. You are come here to learn a method actually. That's why we need to learn the methods. We are not here to memorize the theory, because you can easily search for theory nowadays. You can go to Google and then search for any theories and read about it. But the methods is the one we want to learn in the classroom. So I'm not going to spend too much time on the theory part. I just briefly go through it. At least you understand some of the power factor, like the power factor of this thing. I'll just briefly go through it. So my main focus is on the methods. All right, I think time is up. I think we have 3 students. 2 for pending, I think. Okay. So if you have a question, you can stop me anytime. Because today I think we have not many students here, so we can I can cater for all your individual needs. Okay, let's see the recording is now on. This is very important. Otherwise, I need to redo it again. All right, let's get started now. So before we begin, I think we still need to go back to unit 3 a bit cover in unit 3, especially the this part, the AC waveform and the phasor diagram. We need to look back a bit. I'm quite surprised that they split this one into 2 units. So I think if they put it together under 1 unit, I think it's easier to learn. I think these are the thing I'm talking about. The phasor diagram. I think this one should appear in unit 3, unit 4. Should be here in this unit. All right. So basically, in this unit 3, so this is unit 4, section 3 is section 3, unit 4. We're going to spend more time on this. Where is it? The single phase circuit. Okay, the 3-phase circuit is a theory, or just a theory only. But the single phase circuitry is where we're going to spend more time in. Yeah, and this one also, complex power also. Okay, the transformer, all these are just a theory part. All these are just a theory. Probably we do not have time to cover until the last one. We're going to leave it to the next the following tutorial. All right. So what is power factor? Power factor is appear in the electric circuit because most of our load consists of the inductive and capacitive load, mostly inductive load. Due to this reason, let's say we have one AC power here. You can imagine in your factory, we got AC power, example the 415 AC power, right? We got 415 AC power. Okay, and then in the factory, mostly all the machinery powered by the AC motor or induction motor. Inside the motor, we have all the inductive load, just like this. Okay, and also part of the load also is a resistive load. Okay, and sometimes not sometimes, sorry, it also consists of the capacitive load. Okay, so what happened is, for the inductive load, we're going to have a phase shift issue. The voltage and the current, they are not appear on the same phase. Initially, we think that when the power generated from the power plants, the current waveform and the voltage waveform, they are in phase. You can see there, right? They are coming out from 0. They start from 0, go above 0, and then they drop below 0 at the same point. You see, so this is called the in phase. Right? This is called in phase. This voltage, this current. Usually voltage is higher than the current, right? Usually current is about 50 amp or 30 amp, but the voltage is 400 volt. So it's usually appear much higher. What happens is when the system consists of inductive load, the voltage and current, they are not in phase. The current going to be we call the lagging, just like we used to call the turbo lag, right? Lagging. Voltage will not change. For the inductive load, more precisely, we is here. More precisely is, you need to call it a pure inductive. For the pure inductive, no resistance or the inductive load. This is the voltage, stay the same. Okay, the current will be lagging here. You can see the current is lagging. Okay, to the right hand side here. Here's a 0. So there's a certain degree of delay from here to here. This is the phase difference. We call the phase difference. Usually it's called the delta. Okay, usually called the delta. So this is a current. This is a current. So you can see the voltage first rising up. Later on, sometime later, the current also follow going up, right? So they are, you see, when the voltage go below 0, the current still not go below 0. The current going to take a while, then go below 0. So they are not in phase. So due to this problem, they are not in phase. This phase angle determine the power factor. So the power factor, this phase angle, if you take a cosine of this angle, you take the cosine of this angle is equal to the power factor we are talking about actually. Is equal to the power factor. Okay. So if this angle, let's say this angle is 30 degree. Let's see. Let's take a look. We have let's say we have 30 degree cosine. So the power factor is 0.86, right? 0.86 is considered just not so serious. If the power factor go to the 0.5 or less than 0.5 or anything close to 0.5, so it's going to be very serious issue. Very serious for the TMB, the company that supply the electricity, because they're going to supply more power to fulfill your needs. But your energy meter is based on the kilowatt. The design of the meter is calculate the total kilowatts. How many kilowatt you have been using throughout certain period. Let's say within this 1 second or within this 1 hour, how many kilowatt you are using. But the power TMB need to supply due to this phase shift, it's going to be more than this value actually. Actually, we have another methods to calculate this value. Okay. So here you take, for example, let's say the power factor, you have been told that the power factor is 0.85. So you can calculate the phase shift, right? 0.85. So we let's just practice. What is the phase shift for 0.85 power factor? Okay, let's try to solve this problem. Where is my okay here? Okay, so this is a formula, right? So now we know that this is here is 0.85. Okay. Now let's work backward. What is the delta? Okay, so what you do is we type 0.85. Okay, then this is Windows 10. So you click this trigonometry. You click this second to convert to second menu here. So we take the inverse cosine. Okay, because we are working inverse right now. Go backward, inverse cosine. So the phase shift is 31.779. So this phase shift here is a 31.79. So just take the example. Go back to example again. So if the TMB tell you that your factory has a power factor of 0.85, so you can calculate 0.85. You just take your power consumption. You can work reverse 100 divided by this value. So TMB need to supply this called the they call it apparent power. TMB need to supply 180 kVA. VA is a voltage time current, right? Voltage time current. In order to provide the factory 100 kilowatt of energy or power to run the machinery, right? To run the machinery. That's why, in other words, TMB need to supply 18% more to the factory, and then this will cost them, increase their costs. And if I remember in Malaysia, if the factory's power factor is below 8, they're going to penalize the factory. They need to pay a certain fees if the power factor fall below 0.8. I think I remember 0.8. I haven't actually look at find out the real number, but something near the 0.8, I think. Could be 0.85 also. So just now you know that the thing causing this issue, we call the phase shift issue, is due to the inductive load. And then in nature, in the electric circuit, the inductor and the capacitor, they are actually work opposite each other actually. What do I mean is, when we have more inductive load, the current going to be lagging. In order to solve this problem, we can use a capacitor. Because capacitor is opposite to the inductor. Later you can find out about the formula also. One is the inductor is J omega L, right? To convert their impedance. And then for the capacitive is J omega C, but it's a reciprocal. It's a reciprocal of this value, 1 over J omega C. So you think that, so from here we can know that they are opposite each other, right? They are opposite each other. Okay, in mathematics we call the reciprocal. So when we have this inductive problem here, if we add the capacitive to the load, okay, we just add in a parallel to the load here. Actually, we can bring the voltage towards this direction, so that they are kind of like close to each other. Okay, because this capacitive will make the voltage lagging. So when initially we have the current lagging, if we can make the voltage lagging also, hopefully they can increase again. Okay, so this is the only solution to this power factor issue. You know, in the market, sometimes you can see someone selling something called the energy saver. They claim that the product can save your money in long term by reducing the total power consumption. Actually, it's based on this theory also. Because in our house we got the aircon unit, right? The aircon units are mostly inductive load due to the coil in the compressor and the fan motor, right? So the energy saver just use some of these really small capacitive load adding to your AC socket, and hope that you can balance the you can close this gap to reduce the power factor. But the capacitor is quite expensive actually, and it's quite bulky actually. To match each other so that you close this gap, you need a really large capacitor bank. We call the bank because it's so large. We call it a bank. And the unit they are selling is quite small actually. You can hold it with your hand. You can hold it with one hand in your palm. So it's not going to make any significant result or effect on the output. So it's kind of like cheating actually. In other words, because the capacitor inside the unit is too small to cause the to bring back the to close the gap here. Okay, so this is some basic lah. Okay, this is some basic here. So this is the theory part. I'm not going to go through it. Okay, but you need to also need to pay attention to this how we calculate the average power. Okay, how to calculate the average power for different load here with the resistive, inductive, or capacitive, right? But in the real world, most of the load they are kind of like mixed, no, not just a pure capacitive or pure inductive. They are kind of like mixed. Kind of like your question number one. You see, the load, all the load we call the impedance, they are missing of all the is a mixing of this inductive, resistive, and then inductive and resistive also, and then capacitive, right? They kind of mix all these different type of load here. So the chances of the load just pure inductive is very low. So this equation is almost useless. You can hardly find any load that is a pure inductive. Even though in the AC motor, we got a high inductive load, but in the magnetic wire, the copper wire also got a number of some amount of resistance in the coil. So they are kind of like can present them in this in this way, L and R in series. Okay. So basically, this is just for the classroom only use. All right. Okay. So this also you see that determine the average power. He didn't mention this is whether this is the pure resistive or pure inductive, right? So we just presume this one to be a resistive here, pure resistive, the first one, because inductive load is a cosine 90 degree, capacitive is opposite, right? Cosine negative 90. Yeah. So we presume that this one is the pure resistive, just like your heater or oven heater or water kettle, the kettle, right? So it's not mentioned here. So we just presume, we presume is the resistive load. Okay. Later, I know we go into this part also, the phase shift issue. Okay. Now we come to something quite new to some student. The first time they see this kind of format. Okay, S equal to P plus JQ. So what happened is, you take a look at this figure here. We get this is a complex number. The first one represented by the P is the our resistive load. We call the P. We call the real power, and then the following they indicated by the JQ. JQ is a mix of the inductive and the capacitive load. Okay, it's called the Q. That causing the phase shift. So you can understand this one by drawing the phasor. You can imagine something like this. On the x-axis, without any anchor, right? Without any anchor, let me use a different color here. Without any anchor, let's say this line is on this x-axis here. It's called the P. It has a magnitude of P, 0 degree, right? So if the total power here, we got certain phase shift here, right? Phase shift due to the some angle, right? We got some angle phase shift, right? Delta. Here's what I show you. So the vertical line is going to be, this vertical line is called a Q. Okay, Q is a result from the inductive and capacitive load. This is why we have a phase shift here. And then this y axis in the phasor is called the imaginary. We call the I imaginary. Here is a real power. Real power in a kilowatt. So here is the kilowatt. Here's a kilowatt for the P. So we write P, real power, okay, plus or minus the imaginary. Here is also called the Z. JQ, they call the JQ. So we write J imaginary Q. Okay, and then the longest line here, the resultant power is called the S. It's called complex power. Okay, so S, this Q, just now you know that the Q is supplied by the TMB is kVA, right? kVA. And P is kilowatt. How come I write the A here? P is kilowatt. Kilowatt. This is a kVA. This one is kVAR. kVAR. I call it opposite. This one is VAR, reactive power. This is reactive power here. And then the complex power is VA. Here's VA. Got it opposite. Let's do it again. Here is a kVA, the power supplied by the TMB. Okay. Here is called the reactive power. kVAR. Reactive power. Not this. Okay. So the reactive power is due to inductive and capacitive load. So this is total power. Can be represented by this phasor, right? And this the shift. This is the shift of phase angle, right? So I hope in this format you can understand, right? This is why we need to learn this phasor, and phasor is quite, I think, quite useful in this situation. You can find it totally represent the whole system, the real, the reactive, and the complex power. They call it complex power, right? Sometimes they call it apparent power also. They are different names. Sometimes called apparent power. But for the student, you just know that this is the P, the real power. Sometimes they call it true power also. So there are quite many names they interchange each other. Sometimes we call it true power for the kW, kilowatt. It's called the watt, right? Kilowatt. And then we got the reactive power in the vertical line on the y-axis here. Okay. If your load, if the load is only the pure resistive, so it's going to look like this. Let me show you. Let me show you a quick one. If the load is pure resistive, it's going to be like this only. No anchor on the x-axis only, like this. Okay, on the x-axis, this is called the P only for the resistive load. Okay, so if the load is capacitive or inductive, we got this pure inductive. Okay, we got this vertical line here. So this is called the Z and some number here, J value. Okay, and then we can also go below here to the reciprocal, the opposite. is a minus j and some number. Okay. Anything in between here is the we got the angle, right? Angle here. This is totally 90 degree. This is 90 degree. This is why there is no angle, right? Angle is 90 degree. Okay, but this one is the phase shift like 30 or 60 degree here. So this is a pure resistive. I think this one is a pure inductive. This is a pure capacitive. Okay, sometimes they appear in very funny. It's really complex to tell you right now. It's really not appropriate to tell right now. But at the moment, you just remember that this is how we write the this phasor diagram. S equal to P plus JQ. Okay. All right. Let's go back to some fundamentals. Before we talk more about this, somehow they put this this thing after the phasor. I don't know why. Never mind. We just follow the slide. Okay. So for this slide, you just need to know what is the meaning of this S plus P JQ. You need to know why we need to use something like this to represent a system power. Okay, so S is the power, right? P is also power, and Q is also another form of power. This is something to do with the phasor, right? Actually, this is something to do with the power factor, right? Power factor. Okay. Now take a look here. Take a look here. So in case when come to this power, complex power, when the angle is a positive angle, you can tell this is the true power, right? True power or real power. And then we got some reactive power here. And then the angle here, this is called a positive angle. Why we're going to call positive? Because if you look at the graph, if you look at the graph, normal graph like this, okay, we usually start from this line. Actually, we start from the x-axis. If the angle is starting from here, go to this anti-clockwise, then it's called a positive angle. So if you start from here and go clockwise, so this is called the negative angle. Okay, just remember this one. Go positive, go anti-clockwise is positive. So here you see this angle is go positive, right? Go positive. This why is called the positive angle here, represented by the positive angle like this. Okay, and this angle is due to the impedance, due to inductive load. Inductive. You see the word. This word is very important. Okay, and then the other type of load opposite to this one is called a capacitive load, and then this angle is negative because it's pointing downward, right? So clockwise is a negative angle. So that's why we say that if you have an inductive load, you have inductive load problem, you just apply some equal amount of the capacitive load. You can balance each other out, right? There's a how we present the whole thing here using this triangle thing. They call the power triangle. Okay. Now let's look at the power factor again. So you look at this question. You say the load is absorbing consuming the 2 kilowatt. So 2 kilowatt is a P, right? It's a P. And then the power factor is given a 0.9. Lagging means the due to inductive load, right? Okay. First, by using this 0.9, we can find that angle is 25 by doing the inverse cosine. We know there's a 25 degree here. And then P, our real power, because I look at the unit here, kilowatt is a real power, is on the x-axis without any angle. This angle is caused by the reactive power. We call the Q. And then this is the angle 25 degree here. So that find the complex power. So the complex power is this is the longest line here. And this is equal P plus JQ. P is 2000 2 kilowatt plus JQ. So we need to find the Q by using this formula, the trigonometry. The Q is equal to the second longest line. This is the longest line, right? This is the second longest. This is the longest. This is the second one, right? So the P is equal to Q is equal to P tangent. These three are tangent, right? Because this angle is facing this Q, so it's tangent, right? And then we take the P, Q, tangent theta. We can calculate the this reactive power is 900 something, right? So you can represent this complex power, this longest line here, called the S here. Copy and paste here. Okay. Here is S. Here is P. Here is Q. So we write the whole thing here. We know the P first. P. And then this one we found to be positive, right? 3 plus J and this number, reactive power. VAR, right? Voltage current reactive. So this is this number here called the Q. Okay. And we also can convert this one to the phasor unit, the phasor form. This is a rectangular form. This is called the rectangular form. Okay, rectangular form. To convert to phasor form, okay, it become take this one square, and then the square roots to get this number. Okay, this one is using the tangent. The tangent of this one and this one, you get the 25 degree, 35.84 degree. So this is the phasor form. And as a student, you need to be able to convert here to here, and from this format to this format also. The reason why is this format is easy to do the plus and the minus. Okay, example, you got a V1, you need to plus V2. You can use this rectangular form. In case you want to divide V1 divide by I1, okay, when you do the division or multiplication, it's better to use this form. Okay, because you can just directly divide this number. Example, now without the pen is very difficult. Let's say you got one phasor form like this. Let's say you got the H, you got 50 degree here. Okay, in phasor form. If you divided by 2, I pick a very good number here. Divide by 2, 30 degree. So this is a division, right? Division is better to use the phasor form. So 8 divided by 2 is better 4. And then 50 and 30 is a minus, right? So become 20. 50 minus 30, we get 20. So it's really easy to work out the result for this division if you're using the phasor form. You cannot use a rectangular form to do the division like this. Okay, so we need to convert. In case we need to when we need to do the addition or subtraction, we use the rectangular form. When we come to this division or multiplication, we just use the phasor form. So sometimes we need to convert from here to here or from here to here. Okay, so you need to be prepared. Okay. All right. Now we look at the real fundamental here. This will also cover in the unit 3, the previous unit 3. In this is unit 3 actually. I'm showing here is a unit 3. I mean, unit 3 you learn about this format, right? This is the how we represent the waveform using this mathematical equation. Okay, let's look at it again. Use a quick review. Okay, let's start with something. Okay, let's start with the Malaysia. In Malaysia, as you know, our AC power is 240, right? In the household AC power, they call it 240 V. They call AC, right? Alternating current. And then probably the other thing that they give you is in Malaysia is a 50 hertz, right? Singapore is a 60. We have 50 hertz. Okay, so what does it mean actually? Can we convert this to others format, which can better represent the system, easy to understand or useful? So when you try to plot this one on the graph here, you know that in Malaysia, the voltage we are talking about 240 actually is a RMS 40. And then we know that it's a sine wave, but from here we don't know it's sine wave, right? But from the fundamental, we know that the power we receive in our wall socket is a sine wave or cosine wave, right? So we can just use a sine wave because the sine wave and cosine wave only different in the phase only. Here's a sine wave, okay? And this sine wave, we have a positive peak here, maximum point, we call it sometimes they call the V maximum or VP. This one is a negative V, right? Here is negative Vm. Okay. And how about this? How about this? 50 hertz here. So this 50 hertz tells you the how many times. Here is the time, right? How many times this one will repeat itself? How many times? So 50 hertz means 50 times in 1 second. So this is a frequency. Frequency equal to 50. Okay. And to convert to time is equal to 1 over frequency, 1 over 50. So we get 0.02. We get 0.02. Within one cycle or one period, the time here is called the big T. Usually the symbol is T here. So the big T here for one cycle is 0.02 here. At this point, 0.02. Okay. In one cycle, if you try to convert to degree angle is 360 in one cycle, right? One cycle is 360. Okay. If you want to convert to radian, the radian is here's a pi. This is 2 pi, right? 2 pi is one cycle also. So there are a few formats we can use actually. Okay, so this is a basic thing here. So how to write the mathematical equation for this waveform? You should know, right? This equal to the maximum voltage multiplied by sine omega t sine omega t, right? Omega t. So what is this omega actually? This omega is equal to 2 times pi, 2 times pi and frequency. So in Malaysia, it's 377, right? If you type the 2 times Malaysia 50, wait, time pi. Wait a second. Time pi. So in Malaysia is 314. Okay, this 2 pi frequency, right? 2 pi frequency, 50 hertz. Yeah, correct. So the 314. So it's in Malaysia, you should write VM sine 314 T. So this T, this value can tell you the frequency component. Okay, you can find the frequency from this number 314 by work reverse. Okay, if you work backward, 314 you can calculate what is the frequency. Okay, sometimes in the test they just give you Vm sine 2t. Then they assume you to find the frequency from this number here. Okay, and let's work out the Vm. So in Malaysia it's a VRMS, this VRMS. So the Vm should be higher, right? Vm should be higher than this 240. Vm is the maximum point. So the Vm for Malaysia is square root of 2 for single phase times 240 and 240 is equal to 345, I think. 2 square root times 240, 339. I always remember. Okay, this 339. So the correct way to present Malaysia AC power is 339 volt sine 314 T. So if we have a power factor issue, let's say we have a shift of this waveform. Let's say this waveform now shift 30 degree. This voltage waveform now let's say okay, now it's a voltage waveform. Let's say it's shift by 30 degree. Delay kind of like lagging 30 degree to the right hand side. So this one we rewrite again 339. We rewrite again. Let's use a bigger phone here. Okay, 339 times sine 314 T minus 30 degree. So this is a correct way to represent if we have a phase shift in our waveform. So you should know where this come from, and where this come from, right? Okay. Another one you need to learn is the frequency component here. This T here is equal to 2 pi over omega. Okay, here's omega, right? Omega. And 2 pi f, if you bring this over, omega is 2 pi f, right? Omega is, using the mouse is very difficult. So omega is equal to 2 pi times the frequency, right? 2 pi f to pi f. So the one period is equal to 2 pi over omega. Okay, you can work this out by playing around with this number. Okay, I'm going to give you a quick exercise right now. We'll kind of like I give you about 2 minutes for you to work out. Okay, and later on we find out the answer together. Okay, let's try one example here. The voltage as a function of time is 12 cosine 50t plus 10 degree. Okay, this is given one. This is given. This is degree. So I want you to find. First, I want you to find the amplitude. V, or we call it Vn. Okay, Vn, amplitude. How high the voltage will be. Okay. Second, find the phase. Third, find the frequency. Okay, and then find the period. Also, the last one is to find the angular velocity. They call it angular frequency. Okay, I give you about 2 minutes. You can try yourself. Okay, so when I come back, I'm going to show you the answer here. So take this one as a practice to convert this format to find all the detail from this equation. Let me take some water. Okay, let me show you how this one looks like on the graph. So you know the cosine start from here, right? This cosine start from here. Okay. So this is a cosine. This is cosine. Cosine theta, right? So the plus 10 means going to this direction. Plus means leading. Okay, so going to this direction here. Let me use a different color. Right? Let's go more towards the left-hand side here. So this red color here is this cosine. It looks like this, okay? Shift 10 degree to the left-hand side. Minus is the lagging delay. Going minus is going this direction. If this one's a minus, it's going this direction. Okay? They mean lagging. Because this is time is going this direction. This 0, 1, 2, 3, 4, right? Okay, this lagging, and then this before 0 here is leading, right? Okay, this is how it looks like. So the amplitude is simple, right? Amplitude, you just take the 12 volt tail is the amplitude. So answer here is 12. 12 is the amplitude voltage, the maximum voltage here. Okay, so the phase is here 10 degree. The one called the phase is 10 degree. The frequency is coming from this figure here. The frequency comes from this number 50. Okay, but this is the if you can calculate the period, I think it's easier. The period is 2 pi over the omega, right? So this is omega. Here's omega. Omega t, right? Omega t. So we take the 2 pi over 50. Okay, the answer is 0.1257 seconds. Okay, if we know the period, it's the whole period here, one cycle, and then the frequency is simple. Frequency is 1 over period. So the frequency is 7.9 hertz. So what is this angular frequency? Angular frequency is this omega 50. 50, but in the radian per second. In radian. 50 radian per second. Okay, this is the answer. Amplitude come from here, phase come from here directly. Frequency we need to calculate 1 over t, but we cannot find the t here. So better for us to find the t right here. 2 pi over omega, because this is omega. We can calculate t. This is why sometimes this equation is quite useful. Okay, and then the angular velocity is here. You just need to remember the unit here, radian per second. Okay, let's go back to the one more example. It's quite important. Now I try to explain this part here. Okay, let's look at this number. Let's look at this number. Let's look at this example. So we have voltage V1 and V2. They are given one in cosine format, one in the sine format. Right? One is using a sine, one using cosine. This one with the positive phase shift, this is a negative phase shift. So we want to know which one leading which one, right? Is a V1 leading V2 or V2 leading V1? By how many degree? Okay, I'm going to show you one good method how to solve this problem. Because when you come to classroom, is where you learn the methods. It's not to ask you to memorize certain thing. I want you to learn this method. How to find which one leading which one. Okay, to solve this one, first you just need to draw a cross here. Starting by draw a cross here. And you need to remember, when it comes to the AC system, the cosine, we put the cosine here. Put the cosine here. And cosine and sine are separated by 90 degrees, as you know. They're separated by 90 degrees. So sine is on the x-axis, cosine is on the y. Cosine is on the x-axis, sine is on the y-axis. Okay, we just start from drawing this cross here. Now we do the most simple one. V2 sine minus 15. So this is a 0 point here. Okay, from here, go this direction, anti-clockwise direction is positive. Okay, so positive, go this direction. Positive, go anti-clockwise, counterclockwise. Negative goes clockwise. So this is phi. This is the amplitude. Amplitude is phi. So I use a red color here. So let's say the length here is phi. Okay, this is phi. And here we go in this direction. This direction is minus 15. Minus 15 degree is go this direction because it's minus. Minus is going clockwise. Okay, so this is our V2. V2 is simple, right? V1 is a bit complicated. V1 is a cosine. Cosine is okay here, but it's a negative cosine. Negative cosine means opposite the amplitude. So we can just draw one guideline first, okay? We just draw the one without this negative one. So we just draw the cosine plus 40. This is plus 40 here. I use a light blue color here. So here, let's say here's plus 40. Because plus going anti-clockwise, right? So this is the V1. Okay, V1 positive. But this V1 is negative. So negative is opposite here, the other side. This side. Here is 40. Here is 40. So this is a real V1 because it's a negative value. Just now this one is just a reference only. I just use this one as a guideline. Okay, this plus V1, this is a negative V1. Because V1 is negative. You put the negative over here, this is negative V1. Okay. So let's see which one leading which one. The answer is really clear, right? This is a 0. 0 point is here. So V2 will be the one to reach the 0. V1 will be later. So it's a V2 leading V1 answer, okay? And then the difference is this here. Here is the 15. Here is the 40. What's the difference here? You take the calculator. Total is 90. 90 degree minus 40 minus 15. So we left 35. So here's 35. Separate these two line. So V2 lead V1 by 30, 35. So if you look at the answer again, if you look at the answer, oh, what happened? Can't. Look at the answer here. You need 3. So V2 lead V1 by 30 degree, 35 degree. This is how it comes from, right? So you can use this method. It's not easy to memorize, I tell you. So I better show you this method, how we represent the whole 2 voltage here on this graph, on the radar graph. So it's easier for us to visualize which one leading which one. So here's 0. V2 is faster to reach this line than V1. V1 will take longer time to reach this line, right? Because going this way is a positive, return to 0, right? Okay, so you can kind of practice this one. I'll give you another one to practice. Okay, let's find one question to practice. I give you another one to test your understanding here. Okay, let me find the okay, you got V1 here. V1 equal to minus 10 cosine omega t plus 50 degree. V2 is equal to 12 sine omega t minus 10 degree. So you need to find which one is leading which one. This is a degree. Which one leading which one? Which voltage leading which voltage? Okay, I give you some time to try. Okay, later on we need to later on focus on your assignment, because all this is related to the assignment. Okay, ready? Let's draw the cross first. Okay, then the x is cosine. Need to practice it many times so that you can keep it in your mind. Okay. Let's start with the something without the negative first. Okay, these are all positive. Here's positive. It's easier, right? So sine is here. Minus 10 is go clockwise. So this is V2. So V2 is here. Let's use the blue color. V2 is here. This is the length. The length is 12, right? So this minus 10 here. Minus 10. Degree. Okay. It's not easy to write a small circle. Minus 10 degree here. This is a V2. Okay, for the V1, let's use the red color. V1 is a negative value. Let's draw the reference line first, okay? Cosine plus 50. So here's cosine plus 50 is here. Let's use the light color here. Let's say this plus 50. Okay, this is a V1. But this one, V1 is positive. So the negative value is just opposite each other. The opposite is a V1, right? So this angle is a face to face, right? Each other. 50 here. So here's V1. Now, of course, V2 lead V1 again, right? V2 lead V1 again. So the difference is what? Difference is 30. 30, right? So the answer is, let me check the answer. V2 lead V1 by 30. Okay. V2 lead V1 by 30 degree. So this is the answer. So I hope you can learn this method. If you find this method is easy to determine which one lead which one, right? This is very important. Okay. And I hope you come here to learn, not to memorize something. To learn some methods. Okay, so this is the answer. V2 lead V1 by 30 degree. Okay. Now I kind of prepare you for the assignment number 2. The next thing you should learn, if you want to solve this problem, okay, the next thing you should learn, just now we talk about the phasor, right? We talk about the phasor rectangular form. Okay, let me follow this tutorial here. Just now you know that the in phasor form, let's draw the let's draw this. The line is too thick. Let's draw this. Okay. And as you know, here is a real power, right? Here's a real power. Real axis, we call the real. Okay, we call the real. Let's say we got 1x. Okay, let's say you are given x plus jy. So where is x? X is here actually. Here's x. See a thicker color here. Here's x. Same as the power. Okay. Y is where? Y is a imaginary. Here is an imaginary axis. Here's IM imaginary. So Y is here. Yeah. Here's Y. This is very important. Even though I repeat 2 times already, this is very important. Okay. Here's Y. The height. Okay. If you look at the triangle, this is a height, right? And here is we call the R. Let's call this one R. And let's say here we got 1 angle here. So this is called the rectangular form. This one you should learn, right? This is called a rectangular form. The other one is called the polar form. Polar is R at certain degree at this angle. Okay. So what is R? R is trigonometry square root of x squared plus y squared and then a square root. I repeated. I did it again. One more time. R is equal to x squared plus y squared and then the square root. Oh, what happened? How come keep making mistake? R equal to x squared plus y squared and then the square root. Without the pen, it's very painful right now. Square root, okay? If you take this square root, this square, and then the square root, you can find the R. This is called the polar form. Okay? Another form we are not covering in this tutorial is the exponential form. It's a R exponential J theta. So this is called the exponential form. This is not very friendly. That's why we are not keen to learn this format actually. So we just focus on these two or this unit, okay? Okay. Then the student can come back later to watch the video. I think the video is recording, right? All right. So we are not learning this right now, but you can go online and find the tutorial. Okay. We are just focused on the integral and polar form. So, okay, to convert to x from here, x is equal to convert from here to here, r cosine. Oh, let me type better. Let's type. Is equal to r cosine theta. Okay, r cosine theta. Actually, I can type O. R cosine theta is x. To convert to y, it's about the same thing also. Y equal to r times sine theta, right? This is the theta. So you could convert from here to here, here to here. How about the angle? If convert from here to here, how to find the angle? The angle using the tangent, right? Reverse tangent. And the angle is equal to reverse tangent the imaginary over the real. Y over real. Y is the imaginary because of the z. This over this, okay, tangent. But you need to use inverse tangent here. Inverse tangent for the theta. Okay, this one you must remember for, I think, for life. This is how to convert from here to here or from here to here. Okay, if you're ready, I want to give you one exercise to convert from one to another. Okay, let's try one exercise. Let's try one exercise. Okay, 40 polar form at 50 degree. Okay, plus 20 at minus 30. Okay, let's find this one. Let's practice this. Okay, I gave some time to practice there. Okay. This one, from polar form to rectangular form, because why we need to convert to why we cannot just do it right away, do it just multiply each other or add each other, because this is a addition. Addition doesn't work with the polar form. Okay, polar form is not easy to add together, so we need to convert to rectangular form. Remember, just now I said the plus or minus, you need to use a rectangular form, right? Rectangular form, and multiply and the division, and you use the rectangular form. I use a polar form, use a polar form. All right, so this one convert to rectangular form because of the plus here. Rectangular because of the plus, okay? So this one convert to 25.71 plus J 30.64. Okay, and this one convert to rectangular become 17.32 plus J 10. Okay, then you can just add them up, right? This one add this number, the real add the real number, the J add the J number, and then the answer is 47.72 plus, anyway, it's not 47. It's 43. 47 come from? 43.03 plus J this is a minus J plus J 20.64. So here minus, right? Minus here convert to minus. Here's a minus. So 30 minus 10 become 20. Okay. Here's a minus. Okay, now we convert this one back to polar form because this is given in polar form. Now we need to convert to polar form is 47.72 at the angle of 25.63 degree. Okay, because given in polar form, answer better in polar form. Okay, so I hope you understand this practice why we need to convert to a rectangular form because it's a plus. Okay, I'm going to give you another one using the multiplication or division. I think you should understand, right? One example is enough. Okay, let's look at the next example. We are now very close to to answer this question. One step closer. Okay, let's try this one. I want you to learn this one. Let's say you're given I equal to 6 cosine 50t minus 40 degree ampere. Okay, another one is V equal to minus 4 sine 30t plus 50 degree volt. This is a degree. So I want you to convert to phasor. It's called phasor. In polar form. How to extract the data from here to convert to just now we have seen the polar form, right? Just now we have seen how the polar form looks like. How to convert here to the polar form. Okay, actually this answer is quite straightforward. For the eye, convert to polar form, usually we write the capitalized. We write the cap I is equal to, this is the amplitude, right? This one actually is the R. So we take the 6, and then this is the phase, minus 40. So it's straightforward, right? Straightforward. Easy, right? From here to here. Sometimes you are given here, like this in the exam, you need to convert to this, okay? Let's try the other one. The other one is a bit tricky because we are given a negative here. Okay, we're given a negative here. So in order to take away this negative here, we need to convert to cosine. Let's convert to cosine to take away the negative here. So let's draw our cross again. This is a minus cosine here, somewhere here. This is a sine, remember? Cosine is right here on the x-axis. You see, to convert from sine to cosine, we need plus 90. From sine to cosine, using the same graph just now we're using this, right? You can see sine is here. If you are from this point, you want to come to this point, you need to plus 90. Okay, let's convert to cosine now. By using this, it's easy to visualize. So V will become, convert to cosine, become positive. Okay, the negative 4 will become a positive. This is a negative 4. This is not a typo. This is a negative 4. Will become positive. Cosine 30t is still there. Frequency doesn't change. Plus 50. And then plus 90. So the answer is V is equal to 4 at angle of 140. Okay, I hope you can using this method we learned to convert this one to phasor. All right, let's continue. Let's look at this question now. Oh no. Before we look at this question, we better look at the PowerPoint slide first. Okay, we look at the PowerPoint slide. In this, I think you are already familiar with all these figure, right? With all these symbol, omega, VM, all this thing, right? Now become familiar. And also T, F, and the angular frequency. Okay, I think you're already familiar with all this. How to come to this number, how to convert to frequency, how to write in the mathematical form. Okay, this waveform. Okay, I think you're familiar. Just go straight to this Okay, let's go through this one. This one is in this circuit we have got AC power, probably the voltage in this format, right? In this format, Vn sine omega t, the power, and then they apply to the load pure resistive only R only. So the current is just a V over R. V is this thing over R. Just nothing new here. Okay, everything as. And then as you know, on the phasor diagram, the real power is on the x-axis, right? No angle, right? No phase shift, no phase shift. They increase at the same point and go to zero at the same point. They start at zero at the same point and go to negative number at the same point. So on the phasor is a x-axis. So nothing new here. So all these average power we have to skip right now, okay? Because we need to focus on the assignment number 2. So for the pure inductive load, one thing you need to memorize the inductive load. We have something called the impedance. So the impedance is the impedance for inductive load. We call the sometimes we call the X, right? We call the reactant, right? It's equal to omega L. Simple, right? Omega L. Okay, it's some kind of a resistance, what we call the reactant. Okay, so this is a 2 pi frequency, right? As you know, this omega is a 2 pi frequency. We already talked about this many times. So by using this simple equation here, we can work out the we don't need this anymore. We can work out the voltage and current, okay, later on. And this average power we can skip right now. Okay, and then we know that for the inductive load, the current will be lagging, right? The current will be lagging in the inductive load. You see the voltage here, the current is lagged by this phase, right? This degree lagging. This is current, right? The lower waveform here is a current. Start from here, voltage start first, then later on current start. So it's a lagging. Okay? The C is opposite. The C is opposite of the L. For the C, the capacitive load, current is leading the voltage. That means voltage lag the current. Voltage is lagging behind the current. Okay, voltage is lagging behind current for C. They are just opposite. Because before that I already show you for the reactant for the C, right? Capacitor is opposite. Because of this reciprocal 1 over omega C. 1 over is already opposite of this thing, right? That's why they work opposite each other. Okay, so all this is the same thing. All right, let's look at this circuit now. Now we are one step closer to our to this question. It's also in series, right? This is also in series. The impedance, these are the 3 impedance here. So now we have only R and L, and with one AC power current. So this is current, this is voltage, right? So somehow we need to add these two become one. We call the impedance, the total impedance of these two load. So R is just a pure one, pure resistive, just square R. But for the inductive load, we need to use the omega L, as you know, right? Just I already write here, omega L. You square each other, then you can find the total impedance, Z, okay? Total impedance is Z, right? Okay. And then the rest is you don't have to worry about this too much, okay? The rest is quite simple actually. The thing I want you to remember is R and L in series, the total impedance is R squared plus omega L squared and then the square roots. Okay, this is the total impedance. We call the Z actually, the Z. This one you should know. Okay, let's skip all this average power thing. Okay, they are not so not so useful. Okay, now we come to the R and C. R and C, as usual, this is wrong already, right? This is wrong. This should be a Z. This is a typo. This should be a Z. Okay, so the R square for this R and C is in series. R square plus 1 omega 1 reciprocal of 1 or over omega C square. Okay, about the same. Okay, about the same with the inductor. Only this thing changed already. Okay, and here also. Okay, now look at here. So this is a phasor. So something I want to show you is going to confuse some of the student. But I need to summarize something here. For the series circuit, probably this one you can take a look. You don't need to memorize. R and C is series, just like this one. R and C is series. The resultant, the phasor is like this. Negative. Okay. This R value is negative. This is the imaginary, right? Here is a negative degree, right? Negative. Because this is pointing downwards, negative degree, right? This is for R and C. For series, R and L is positive. Like this. This is a real, this is imaginary. Okay, X and Y. And then this is a degree. I'm referring to the phasor here. The phasor. The impedance phasor. Impedance phasor. The impedance phasor. For the parallel, RC, we got opposite is a positive. That's why this one separate the series and the parallel. They are quite. So this is X, here's a Y, here's our Z, right? And this one also I think you can predict also. The parallel RL is going all the other way. Is a negative. Okay, negative value here. But I'm not talking about the impedance, the impedance Z. So this here is a Z value, Y. Here is the Z. It's going. So you just need to know that when in series is in this form, when in parallel is in series is this form, parallel is opposite. Okay, that's why when you solving question in this you see here is in parallel. RL parallel, if you can remember, is pointing downwards here, pointing downwards. After you find your answer, you will be pointing downwards. If your answer is not pointing downward, that means something is wrong. Okay? So here are the combination, RC, RL. If it's series, then should be pointing upward. Okay? Series RL pointing upward. So here, we got the series RLC here. Later we'll know whether it's pointing upward and downwards. Okay? But just now we got one example, right? RLC here. RLC in series, is it pointing outward or downward? Oh, no, there's no answer. Probably pointing outward here. Let me see. There's no answer here. No phaser. You search online, you can find answer immediately. This is R and C. R and C. Okay, well, we're going to do one exercise right now. Let me show one example. But first, we just look at the example first before we do the exercise. Let's look at this example. So we got the L, R and L. Okay, and then we given the frequency. But no voltage, right? No voltage given. Voltage is unknown, but we know the current. We know the current flowing through the R. So if you see that if you see the answer, so the R is the real axis, right? The R is the one without the any angle, right? It's a straightforward. So from here we can extract the V. This V, this current and this one, there's some kind of relationship between each other. So V equal to IR, Ohm's law. Okay, so that we can work out the because R is the one without the any angle, right? R is a real number, real value. So we just can multiply each other I times R without any phasor, right? Without any angle or degree. So we get 120 here. So from here we found this is 120. From these three given values here, we can determine the V. Okay, this is the first step. Find the V, and then find the IL. For the IL, we can use the voltage. Voltage across IL, VIR, right? V equal to IR. This is a Z, right? Z is the impedance, right? Same thing, right? So IL, but I equal to IL is equal to V over Z. Okay, the reactant. So Z is equal to omega J omega L, right? For this L. Okay, just using an Ohm's law, like this Ohm's law, right? VIR. You just treat the Z as an R. Actually, Z is this reactant, right? So by doing this, you can find, where is it? V equal to J omega L, 2 pi frequency is given 400 hertz here. So 2 pi frequency, and this is the L value, 0.25 Henry. 0.25, 200 milli Henry is 0.25 Henry, right? 0.25 Henry. And the J at the denominator, right? When you convert to J minus 1, you put on top here becomes J minus J. This one probably you don't know yet, right? If you go 1 over J is equal to minus J. Okay? So this where this minus come from. And then after you work out this number, you find is a 191 milliampere. Okay? And then from there, you know the minus J means is right here. Minus J this direction. J is positive, right? So minus J is negative. So if you here is a minus 90 degree. From here to here, minus 90 degree, right? Yeah. Okay. Then the final I, to find the main current here, the main current is equal to, using a KCL, this current enter and these two exit, right? One enter, two exit. So this current equal to these two current. This current supply to these two components. So I equal to the main current equal to resistance current plus the inductor current. This one is easier to find, right? This one is given. This one we just found it. Okay, then we convert to polar form. Okay, and we find the angle like this. Here is the minus J here over the this line, the real exit, then tangent. Okay, then we can find everything. So the phasor looks like this. Okay, minus 37 is, it means go opposite. Yeah, this right. Minus 37 means go this way, minus. Remember, go this way is positive, right? If you come from this line to this here, is minus. Here is positive, right? Here is positive. Here is positive. So minus 37 here means negative. So this is a phasor diagram. Okay, let's take one to practice. Okay, before we finally solve this issue here. Okay, let me guide you how to. Let's do one exercise to practice. Okay, so you are given one voltage source here, and then one resistor in series also, right? Same with the example here, in series. Resistor and one capacitor. Okay, here is V equal to, I give you this mathematical form, then cosine 4t. Okay, R is 5 ohm. The C is 0.1, 0.1 F farad. Okay. Find the voltage. Find this voltage VC, capacitor voltage, and the current, and this current. Find VC and current. Okay, you try. Later I show the solution. What is the first step you should try? What is the first step you should take? First, you need to find the impedance. Okay, I'm going to guide you. First, you find the impedance. The total resistance of these two, we call the impedance. So this is easy, right? Phi is just phi. This is a real number, right? So this is just phi plus this is the imaginary, right? This is the reactant, right? Reactant is the one. This is real. Real is phi. This capacitor and inductor, they are on the this imaginary, right? Now we need to find this Z. This is Z. And this is the, we call the XC. For this capacitor here. So if you remember, the capacitor, the reactant is a reciprocal of the value 1 over J omega C. C is a 0.1. Okay, omega is what? This omega 4. Cos something T, right? Without any phase shift, right? Without any phase shift. This form you know already, right? This is a magnitude and cosine omega T is omega. So equal to phi plus 1 over J 4 times 0.1. Okay? Answer is this J, reciprocal of J become negative number, become phi minus J 2.5. See, 4 times 0.1, 4 times 0.1 is 0.4, right? 1 over 0.4, then reciprocal 2.5. So this is simple, right? First step. Okay, second step, we find the current here. Second step is to find this current first. Because later on we can use the Ohm's law to solve for this voltage here. Ohm's law, if you know the current. So the current is very simple, right? The current is, because the current is the total resistance over the voltage, right? I go to V over R, V over Z now. Z we know already, V we know already. So the V is without any phase shift. We can write in phasor form. Then we learned this just now, right? How to convert this into phasor form. Then at no phase shift, right? At 0. And this one convert to phasor. So I told you, right? Sometimes we do the division, we cannot use the rectangular form. So this one convert to phasor. Okay, and then you work out the Z after you convert to phasor. Here's no phasor, right? You will get answer like 1.789 at the degree at the angle of 26.57. Okay, I give you the answer right now. You can try yourself, okay? Convert this one to polar form. This one we already done enough practice, okay? So I'm not going to repeat again. So after you find the current, you can use the Ohm's law to find this capacitor's voltage. So the equation is V equal to IR, right? But now we call it IZ. This Z is a capacitor Z, okay? Let's call it XC. Okay? So this one become I value is here. Okay? And then what is the XC? Reactance C is 1 over J omega C. C is 0.1. Omega is 4. Frequency doesn't change, remember? Frequency doesn't change. Okay? This value here actually, this value is exactly the same. So you get answer is, after you work out, just now the answer here, I is phasor. This one you convert to phasor because they multiply each other, right? If they multiply each other, it's better convert to phasor because I is already in phasor form. Sorry, I is already in the polar form. This is a polar form. Okay, so the answer here, V, I give to you is 4.47 a degree of minus 63.43. You will get a negative degree because this is a minus here. Okay, you can also represent this one in the mathematical form. So the current as a function of time is equal to the magnitude 1.789, and because the thing given the power is a cosine, right? So we follow the cosine. Okay, and then omega t, omega is 40 minus is plus 26.57 degree. Okay, this answer in the mathematical form. Answer in polar form. Answer in mathematical form. How about this voltage? I know you not. I know you how to write to convert this one also. V equal to the magnitude directly take from here. 4.47 also cosine. Frequency doesn't change. 40 minus 63.43 degree. Okay. Sometimes you can present this one as answer and present this in phasor polar form. This one is in the mathematical form. Okay. Because this one is easy to key in, into the program. If you are learning any programming, this one you can use a C program or the other language to key in this one. This one is not easy to key, right? So sometimes we need to convert to this form here. Okay, now it's time for us to come to our real question here. Okay, you take a look here. Here we got one inductive load, another inductive load, and then a capacitive load. Okay, these two are in the series, and 3 also in series. So let me draw you the circuit line now. We have one, let's see I can remember or not. We have one inductive load here together with the internal resistance. For the first one here is 2 ohm. This is 0.45 millihenry. Okay. Another one is same thing, 500 micro, 570 micro in series, and 5 ohm. 570 micro. Be careful, this micro. Another in series, connected in series is capacitor and the resistance 3 ohm. 3 ohm here. Here is 10 micro. Be careful about the micro sign here. They all powered by this given not in the metrical form, in a layman term, 100 volt. Okay, later I'm going to tell you whether this is the RMS or V peak. It cannot be V peak, right? If this is V peak, you already show the VM or VP. 100 should be the RMS, and this is a frequency. Later we can convert to the phasor form, right? To the mathematical form. All this is powered by AC power given as 100 volt, 2K hertz, 2K hertz. Power the whole thing here, the 3 load in a string. This is how it looks like, okay? So what should you do? Of course, they need to find the total resistance, right? Just on the previous example, we only got one current flowing through this circuit, right? Only got one current, because this is only one loop, only one current. We just find the total resistance Z. Using the method we learned. So what I recommend you is the Z is equal to the R total two plus 5 plus 3, because they're in string, right? In string, you can add them up, even though they are separate by the this R and this R separate by this inductor, this R and this R separate by the capacitor, right? But they can add them together, become 2, 5, 3, become 10. Here become 10. And same also for the XL. Here and here. Okay, this XL plus XC only 1. Okay. The important thing I want to show you is this one, you know already, right? We have done so many times. Omega L. This is the reciprocal 1 over omega C. Okay, and the Z is square, right? Square. But something I want to let you know is on the phasor, usually L is here L is here. Sorry, the XL. The XL is here. And then the XC is here. It's going this way, going negative, L going opposite. They are going opposite each other. Okay. Usually, this value is really large. C is very small usually because C usually in the any electrical system is really small, just like this one, only micro only. L in the motor or compressor usually very large. This why usually the difference between these two actually the anchor, we want to find the anchor, usually is this number, big number minus the small number. Is a difference. So here should be negative. Just need to remember L usually larger than C. Okay, to find the difference, we need to, because the resultant, the answer will be like this on a positive angle. So this is large number here. Okay, you can calculate also that this value is much larger than this value. So the resultant, we got only one J only. It's going to be the positive J, not the negative J. Should be positive J, right? Because this number is larger than this number. So the resultant is here. It's a positive J. Okay, so it's a X. Okay, then take a square root. Okay, to find the total resistance here. Okay, I think this is good enough, the hints, because I'll show you the example how to do this already. So what is the next step? Next step, of course, is to find the current I, right? Find the current I. Calculate the total impedance. This one I showed you already. So the total current using the Ohm's law, V over Z. V is given here. Okay, but you need to how to convert to phasor, how to convert to the mathematical form. I think I showed you already, right? How to convert to Vt is equal to the Vmax, right? And then we can assume sine. But we need to convert this form. In this question, we need to convert because here is not given. Whether the sine or cosine is not given. So this form is not required. Okay, it's not required. We only need in phasor form. So let me confirm to you. Right now, this one is the Vmax. Actually, this is a Vmax. The question didn't say very clearly what this 100 volt is. Is it RMS or Vmax, V maximum? And what we need to clarify here is the Vmax. Let me confirm again. Here is a Vmax. V maximum. One more time. Double confirm again. Yes, V maximum. This one is a V maximum. You need to take note. But usually for any engineer, they will assume this one is the RMS. But if I refer to the answer, is a Vmax. Okay, this is very confusing actually, because this is a track actually, right? A track without any information here. I cannot find any information whether this is the RMS or Vmax. So we have to guess, okay? We have to guess. So I tell you now, it's a Vmax here, okay? You don't have to guess, okay? It's a you don't have to guess, okay? I also don't need to guess also. It's confirmed Vmax, this 100 Vm, okay? And this is frequency. So what's the next one? Calculate the angle, the circuit phase angle. Okay, the phase angle you can take the you can take the impedance. For number 3, you can take the impedance here. The total impedance is this Z. Z is consists of R and the XL minus XC, right? XL minus XC. Probably this one will look a bit awkward to you. Why they need to minus? Okay, because they are cancel each other. In the real world, they are work. How they work is to cancel each other. Remember initially I talked about the power factor. When you have a power factor issue, you just add the capacitor to cancel it off, right? So in nature, they are work opposite each other. So you need to kind of like this number minus this number. This is what they do in the real world. Okay, they are in the circuit to cancel each other out actually. Okay, example, you got positive 5. If you do want so much, right? You want to reduce a bit, you just minus 2, become 3. So this is the capacitor, this is the inductor. In nature, they are always opposite each other to cancel each other out. Okay. If you put 2 inductor, then you do positive, you get more serious power factor issue. Plus 9 power, right? If you want to cancel this one, you need to add in the capacitor. So on nature, they are cancel each other. That's why we need to XL minus XC. Because XL value is higher than XC. Okay, that's why we take XL minus XC. If XC value is higher than XL, then you can take XC minus XL. Because we want to get a positive number. Here's a positive number, right? Because we found the angle is a positive. Here is a positive. It's not negative. It's not going this way. It's also true that in the real world, this L is always larger than the C because C is so bulky. I can show you if you go to the website, if you try to find the capacitor, AC capacitor, you can look at the size, and it's so expensive also, and it doesn't last long also. You see, all this value is all in microfarad. You can tell it's all in microfarad, right? I hope you can see all in microfarad. In micro is already so bulky and so expensive. Okay, this one also in micro, right? Where is it? 40 micro, right? They are so expensive in the real world. But the inductor value in the real world is inside the AC motor, AC induction motor, all the coil. Easily you can get milli, all the milli value. Inside the compressor, inside your factory compressor, your fan, your aircon. There are so many of these inductors. That's why in the real world, always XL minus XC. You can hardly find any XC minus XL unless in the simulation. In simulation mode, probably is true. That's why you can always assume this one is true, or 90% is true. Okay. So by doing this, you can find this angle. Because you know this already, Of course, this is the tangent of this over this, right? tangent or inverse tangent of xc over r, right? Here is the denominator, right? Here's the numerator. Tangent for tangent. Right? We learned in the secondary school. Tangent of this theta is this over this. I think this is a trigonometry, right? Let's confirm it. This is called a trigonometry. Yeah. Tangent is A over B, right? A over B is tangent. To find the angle is reverse tangent, okay? All right, now I already show you the part 3. So part 4, calculate the voltage across the impedance. Okay, the voltage across each impedance. So this is a bit a lot of work involved, right? Because there's so many impedance here. What do you mean each? Is it 3, 1? This considered 1, this considered 2, or this considered 3? Because each impedance here, or just this one is individual, this one another individual impedance. So I want to give you the answer now. You don't need to guess, okay? To calculate the voltage for each impedance, okay? What we this is considered one impedance. Let me make it very clear to you. When you all watch the video again, this is considered impedance number 1. This is considered impedance number 2. This is considered impedance number 3. So we have total of 3 individual impedance. Okay, Z1 consists of this L and this resistance. I know you know how to calculate the total, right? The total Z. Just now if you roll back to the previous video, if you roll back to the previous one, I already show you how to calculate the Z for these two values. How to find the voltage? Wait. Just calculate the voltage across each impedance, right? So how to find the voltage? The voltage across the Z1, because these two become Z1, the voltage across Z1, I think you can use Ohm's law, right? VZ1 is equal to V equal to IR, right? IZ1. I you know already, right? We obtain the I from here. Only one I only. Only one. This is a phase. This is an angle. Phase angle. Only one current only, right? In this loop, only one loop only. Okay. At the end, you need to draw the phasor. And most students, they don't know how to draw this phasor. Okay, this phasor is referred to the phasor for the impedance. Okay, this phasor is the Z, total Z, the total R, and the reactant XL minus XC. Okay, I hope you understand this. For the number 4, let's focus on question number 2 now. Okay, so I jump from this. I jump to this is just work using the reciprocal value 1 over just now the R is the IR is this value, right? IR is this value. So the reciprocal is this value, reciprocal. 1 over 255. This is G. Just not the R. Oh, 255, right? Wait, let me see. G. Where did 2.13 come from? It should be reciprocal value only. Wait. But you don't need, you only show this one is good enough. You don't need to show this admittance triangle. Okay. The question asks for the phasor diagram is a normal phasor diagram, not this admittance triangle. Okay. G is 1 over R. B is 1 over XL. Okay. This one is not important now. Let's go straight to the three phase. The three phase. Let me brief you a bit. Three phase. Three phase. We have star and delta. Star and delta system. In Malaysia, usually is the star. We have a load here. Our load usually is the inductive. A lot of inductive, right? Our load and resistance also, right? Star is something like this. Resistance. And this looks like star, right? So on the star system, we know that they have a common point here, common node, we call the neutral. Okay, and this output here is called the line voltage. Line voltage. This is called the line voltage. 1, 2, and this is line voltage 3. And this voltage over here is called the phase voltage. So in Malaysia, phase voltage is 240. Line voltage is between these two lines. Line voltage is 415 volt. The difference between here and here is 215 volt. The difference between this and neutral is 240. The difference between the line is 440 RMS. They all separate by 120 degrees to form one complete cycle, right? 120, 120. Physically, they are separated by 120, right? But on the electrically, they also separate by 120 degrees. That's why when you go back, you see that the first phase is like this. Second phase separate by 120 degrees. The third phase another 120 degrees. So altogether is form a complete 360 degree, right? This is how we represent in the mathematical form. Another possible connection is using a delta. So delta, there is no neutral. They are joining. There's no common also. These two join between these two phase. Okay, there were one node between this phase, another node. This phase, another node. So the way how they join is different, and that's how we represent the in the mathematical form also. Also, it is the star. This is a star. This is a delta. Okay. And besides knowing that, usually we need to work out when this star is power up the star load. Okay, so this is a voltage and current measuring supply to this load. So this current is 5 volt, 5 ampere, and 2.6. So total is 8.2, right? So this is the load unbalanced. You can see the load is unbalanced. 5 amp this way, 8 amp this way, 2.6 amp this way. But this is a bit strange how they draw this. Never mind. If your final exam got this question, I'll show the example. Okay. But right now we have no time. We need to jump over to the transformer. So this is usually how it looks like in the exam question. We got three phase in the star connection. We got one neutral, and this three phase is power 3 loop. So in this time is very beautiful. 3 pure resistive loop. I ask you to find the current and neutral for each loop. Find the current going through each phase. The current going through the phase and current in the neutral conductor to find whether it's balanced or not. Okay. So you can follow this step here. Convert this is called the line voltage, right, to the phase voltage. They call the V phase. Convert to the phase voltage. Okay, you just follow the step here, and then eventually you can come up this triangle here, phasor triangle. Okay, showing each line current. Okay, and then the neutral, we got some current in the neutral. So this load is unbalanced. In this case, it's unbalanced. If the load balanced, because you have the neutral, you have zero current, no current flowing through the neutral. Okay, so but we are focused on transformer. So when come to this transformer, the question is quite straightforward actually. Let me look at the question again. So this question asks you to find the secondary current, asks you to find the minimum value of load resistance. Because this transformer supplying the maximum power kVA, okay, so-called the complex power or apparent power, 10 kVA. So it asks you to find the what is the minimum value of load resistance. Because the lower the load resistance, the higher the power, right? Consume more power. Okay. So and then the last question asks you for the primary current. So what the equation you need actually is a quite basic equation. Let me show you some of the basic of this transformer. So this transformer is kind of like single phase transformer. Single phase, right? Single phase. So single phase is the most easy one. So we have a primary here. We have a secondary transformer. You know how the transformer works, right? They transform the power from this high voltage probably to low voltage, or from low voltage to high voltage by using this mutual electromagnetic field. Okay, you just build them in this way, and then link these two field with the iron core, so that the field can be shared by this magnetic field generated by this primary can be shared by this secondary, and then you can find the voltage here. So the voltage here is depend on the turns ratio. So the turn ratio given is 12 to 1. You can just write this way, 12 to 1 means if here is 12 volt, here will be 1 volt. The turn ratio determine the voltage. And then the equation you can use in this equation is N1. So this is N1. This is N2. So let's write another way, okay? This is a primary turn, MP, over the secondary turn, NS, secondary, is NS, is equal to the voltage at the primary. So they just direct conversion. Okay. Direct ratio. This ratio is equal to voltage ratio directly. So by using this one, you can solve for the first one, part one. You can solve for part one just by using this equation. So it's pretty simple because it's so simple. I cannot show you how the further step. If I show the further step, I kind of review the answer already. Okay, I just let you know, just using this simple transformer basic, you can solve part one. Okay, what is it 10 VA means actually? 10 VA, 10K voltage times current is equal to the primary voltage times the primary current. So here the primary current here. Okay, it's also equal to secondary voltage times the secondary current. This power can transfer from the primary to secondary. Even though the voltage may be different, the current may be different, but the total power should be the same. This 10K can transfer to primary, also from primary transfer to secondary, still 10K VA. Only some losses in between here, but the losses is not mentioned here. So we assume the losses is 0. Okay, for the part 2, you just need to find the minimum resistance here. I can tell you that for the part 2 is using the Ohm's law. Okay, if you still don't know what's the Ohm's law, you better review. Okay, use the Ohm's law. Using the Ohm's law to find the part 2, the current. It's quite simple. No phasor, no rectangular form. Okay, very simple. For the part 3, primary current. Okay, I give you the equation here. The turn or the primary over the turn in the secondary for the current is opposite. Because when the voltage reduce, the current should be higher. When the voltage is dropping, the current will go the other way. Just like your car battery, when you in the short circuit, voltage will drop to 0, current will shoot to maximum in the short circuit situation. So they are opposite each other, right? So you cannot use this. You cannot use this equation. It's totally opposite. So I S over IP is it should be opposite of the voltage. Okay, in logic. So by using this equation, you can find the part 3. Okay, and that's it. We'll cover the rest, the last topic here in the following tutorial number 4. The last one here. I'm not going to rush into all this with the remaining time right now. We better leave this one for the next tutorial. It's called a magnetic circuit. So all the equation is here actually. All the equation is here for the question number 2. So the equation here is not needed. All the equation here are not related to the question 2 actually. Okay. You just need the question here only for question number 2. So I hope you understand, okay? We run out of time now. I think you are should be quite clear how to solve these 2 questions. If you roll back the video to the initial in the beginning where we talk about all this impedance, we talk about all this. The only thing confusing is this one actually. It didn't say it's a VRMS or VPeak. I already make clear to you that this is the VPeak. Okay, but I tell you in the real form, most likely this one is the RMS. We need to convert the RMS. But for this question is VPeak, okay? For this question is VPeak. Because if you want to write in VPeak, this is not how you should write it. You should write in something like this. To indicate something in VPeak, we should write V like this. The voltage is 100 Vm sine example 2t. If you given this format, then people know this is a VPeak already, right? You don't need to. Sorry, one more time. 100 sine 2t, example 2t. This is the frequency, right? If you write in this format, all people know this is a VPeak, right? You don't need to tell anymore. You don't need to explain whether this is VPeak or RMS. But if you put 100 volt here, most likely, most of the textbook assume is the VRMS. So when it's a VRMS, the VPeak become square root of 2, VPeak is higher than the VRMS, right? Time 100. Okay. I mean for most textbooks, this is how we you can also confirm this one with online tutorial. If you say AC power, you see how people write AC power. We just simply pick a few examples. You see here's a VPeak, right? VM. So if the question didn't say it just give you one number, let me find one. Let me find a quick one. Let me find a circuit something. Some circuit. Let me find some circuit. How come why? I just want a basic AC circuit. Yeah, let's example like this. If people put 10 volt and then frequency usually is RMS. If people want to indicate a VPeak, you indicate this way. This is what I mean. Another example or not? See this example also. They put this mathematical form, right, to indicate this VPeak. When it comes to engineering, we like to use this format most of the time. I can't find any good example right now. If you look at this example, it gives you the voltage and the frequency, right? And this voltage, if you look, the answer should be this should be RMS. Yeah, you already said, right? The supply voltage has a constant RMS value, V. That's why I need to make it very clear to you, this is a repeat. But it's not common to express it this way, okay? You just need to bear in mind that it's not common to express RMS in this way. To express a repeat in this format. But in this example is a repeat, okay? Just make it clear again. This for this question, 100 volt is a repeat. I'm quite sure because I refer to the answer. I'm quite sure it's a repeat. Okay, guys. Do you have any question for me? Otherwise, later on you have question, you can just post the WhatsApp. Okay, I try to help you. Okay. So the purpose for this tutorial is to help you go through your TMA2. The first two questions I think should take less than 1 hour, I think. And then you have some time, you need to prepare some time to prepare your lab report here. Simple lab report, okay? Simple lab report. If you look at the requirement here, your lab report need to have introduction, procedure, result, graph. You know, some lab they got graph, some lab they got table. Okay, and then also discussion and conclusion. You look at the weights, the result, the weight is 8, really heavy, right? This one also very heavy, 7.5. If you got time, I suggest you at least, if you run out of time, at least you write conclusion longer than sorry, one more time. You write more discussion than the conclusion, because conclusion only the weight is only 3.0. This weight is 7.5. It's more than double of this conclusion. Some students, they just ignore these two. They didn't write these two. That's why they get a 0 here, 0, 0. When you work out the final, the total mark, when these two are 0, 0, the total score over 100 for this question, if these two are 0, that means you're losing more than 50% already here. Even though you got your result correct, you got your step correct, everything correct here. If you didn't write the conclusion and the discussion, because this excellence is 4, right? 4 times 7.5 plus 4 times 3, if you calculate, 4 times 7.5 plus 4 times 3 is 42. It's almost close to 50%. It's almost close to 50% of this question. One question only 15 marks, right, for lab question. We have 4 lab question, I think. 4 lab question. Oh, we have 5 lab question. Lab 1 to lab 5. We have 5 questions. Each one worth 15%. All to be 100% here. But here is already 42%. Because based on my past experience, many students, they didn't write the conclusion and discussion. That's why I need to mention it here. Okay. If you didn't write a good introduction, the weight is only 2.5. If I give you the certification here, 2 times 2.5, you still got something, right? But the procedure is already provided here. You cannot say you don't the right procedure. If I see no procedure, no step, then I cannot give you I cannot give you four, right? I can give you one only. Most of the steps are missing. So here is 1 only. Because the minimum is 1, I cannot give you 0. Minimum is 1. So 1 times 4, here you get 4 only, 4 marks, 4% only, 4%. So if you include the table, you include the result, the graph, everything, probably you get 3 or 4 here. Time 8. Wow, time 8 become a 32%. 4 times 8, 32%. But if you skip these two, the last two, you lost 42%. So the 42% times 50 marks lost 6.3 marks for each lab if you didn't write these two. I mean, discussion and conclusion. If you skip these two, you lost 6.3 marks for each lab. So you need to take notes of this one, okay? Even though you run out of time, you still need to write something, okay? So that I can give you, at least give you some mark. If you produce an empty space there, I cannot give a marking, right? I cannot award a mark on the empty space, right? So at least you need to write something here, okay? Right, guys, that's all I want to inform you. Okay, so I see you in the next tutorial. Okay, the one last word is your assignment number 2. The due date is 6th of March. Looks like the one week later. There's 1 week ahead. You need to submit your assignment number 2. And another important message is the assignment number 2 cannot be extended. Okay, this one you need to really remember it. Assignment number 2 cannot be extended. You cannot request for extension. Okay. This is the WOU policy for many years already. They didn't change this policy. No one's successfully in the past to request for extension for TMA2. No one, I think. I haven't seen any cases yet so far. They are very strict on the TMA2. I don't know why. They didn't give any any information why TMA2 cannot be extended. So just take the remaining times, the 7 days to complete your assignment 2. Okay, guys? I have to say bye-bye now, okay? Any question you post to the WhatsApp, all right? Mark the attendance after this.